Right. Okay. Well, thanks for coming along for the module. So my name's Bill Buchanan, and I'm a professor here. I do research in this area. So you'll probably find in the headlines this week, what was the major vulnerability that was found, where it was advised that you should patch Windows 10. Did anybody pick up the headlines?
The NSA reported that?
It was the NSA, yeah. So if the NSA report things, then you know that something is quite serious. The NSA have a track record for sitting on vulnerabilities and using them. So who knows how long the NSA have actually had this. Did anybody know the detail of what was involved in it? It was to do with crazy things called elliptic curves that we'll be covering later on in the module. And for some reason, Microsoft didn't check the elliptic curve that they were actually using, which allowed someone to take a public key of a website, such as Google, and create the private key from that because of the validation. So I don't know if you see how severe that is. A breach of the trust infrastructure of a company is probably one of the most expensive things that a company has to face with. Something like 150 million average to fix a breach of a trust infrastructure. If you lose even one of your private keys, then you've got to go and hunt all of the things that were signed by that private key. Your website becomes untrusted and so on. So it's a severe problem that we have. So later on in the module, hopefully we'll be able to see what actually happened in that vulnerability. So the module's been created to really tell the story around the complex, intertwined area of cryptography. So we'll try to give you a full picture of all the related areas and not miss out anything, and to give you a foundation that you can build on. So we'll try to build it up through stages in the module so that you could at least understand how secure systems are built from the foundation up. And we'll hopefully see a new world evolving as we look into the future and to look at things like blockchain and cryptocurrencies. We'll see a new world evolving, and it's a different world than the one we've actually built up. Okay, so those are the 10 main units that we're going to cover in the module, and I'll just explain some of the areas. So I think this shows to me how insecure we are, how flawed our basic infrastructure is. So the SWIFT network handles 28 million bank transfers a day. You'll probably find your transactions will be in there somewhere. So between banks, SWIFT handles that exchange between banks and transfer money from one place to another. An unfortunate place in the Bangladesh Central Bank, they had there was a hack where the intruders installed some fairly standard malware. It was used in the Sony hack when Sony lost tens of millions of documents. So it was a well-known Trojan that was actually installed. And what they managed to do was transfer $81 million in an instance. And it was gone. It was not traceable. It's obfuscated in its trace, so it was not possible to get that money back. And then they tried to transfer 20 million, but didn't spell foundation correctly, and they had foundation. And someone in a bank somewhere said, that's not how you spell foundation, and stopped the transfer. So it's kind of worrying that our banking infrastructure, the core of it, is based on simple spell checking and grammar checking. And it's unfortunate because the bank didn't have 24/7 security operations centres and the latest patches and updates and security teams and analysts and threat hunters and so on, because they had things like second-hand switches and no firewalls. Okay, so it's a changing world, and we really need to understand how trustworthy our systems are. And this happened quite recently. So this is on the Ticketmaster website, and then they had a bot that integrated into it, so you could actually chat. And I think it was Monzo called up Ticketmaster and say, you have a problem on your website. He said, well, we don't think we have. He said, well, we are seeing this number of credit card resets, and this is the number of customers that you have on our site. There's an anomaly there. And what it was there was a JavaScript insert into this that allowed, whenever you went from here to put your credit card details in, your credit card details were actually sent off to an adversary. So you got to worry, really, as to the infrastructure we're creating. And this is the BA hack, British Airways. So for 3 months, every single credit card that was entered was sent off through a secure tunnel. And it was this little bit of JavaScript code here that had been inserted. And the great thing, well, the interesting thing about this is that the intruders knew how to create a tunnel. They actually had an HTTPS site already created. So once it was dropped on the site, it was then using a tunnel. So if you understand JavaScript, basically this is a little plugin that allows the interaction from a mobile device, touch interaction, and it had been modified so that whenever anyone put in the details for the credit cards, it was actually sent off to this site here. So don't just trust that someone has HTTPS on their site, that it is actually secure. We'll come on to that later, and what HTTPS is, what a certificate is, how valid it is, and so on. But you can see here, then even adversaries can actually use secure tunnels, and will typically use them as part of their attacks. So now in a GDPR world, so the 4 foundation elements of GDPR is that citizens have rights to the data, like it or not. If you have personally identifiable data on your site, you need to make sure that citizens know how it's been handled and have rights to it. Do you know how long you've got to respond to an incident before you report it? Roughly? 72. It's not long. You've now got to investigate, find out what happened, and put your CEO possibly in front of Sky TV and get them to respond to it. So 72 hours is your instant response. So you've really got to have something prepped and ready. And at the core of GDPR is that we need to encrypt data more. Encrypt it at rest, encrypt it over air, and surprisingly, encrypt it in process. More and more, encryption keys are in the memory of the devices, and it's not that difficult to push out memory to have a little look. So developers just drop a key, encryption key, a private key for your whole company, into memory. Somebody sneaks a look at the memory, and they've discovered your private key. So don't just think encryption is for storing files on a disk at rest. Don't just think encryption is over the air as a tunnel. Encryption now must cover when it's in memory and even when it's in the processor. So it's a core part of really what we need to build is we build an encryption and we need to understand how that encryption actually happens. And the last part of GDPR is what's called pseudo anonymity. I have no idea what that really means. To me, you're either anonymous or you're not. This bit in between, pseudo-anonymity, that the intruder can't tell that this is this person, doesn't really work. Your matriculation number can be easily mapped to your ID. So although we think it's pseudo-anonymized, it's not too difficult for somebody to resolve that back again. So more and more, we need to look at what's called pseudo-anonymity. And in this world, we need to question the usage of wet signatures. So you find that most legal transactions are still based on a wet signature. I can't remember the last time I signed for something with my wet signature. I wouldn't really have any idea what my wet signature looks like. So we need to create a world which moves away from that and towards what's called digital signing to make sure that we can have a trustworthiness in the things that we actually sign. So the world we're looking at is maybe moving towards what's called a tokenized world. In this way, we can have things like payment tokens. So we can pay through cryptocurrency if we need to. Why does fiat currency even exist in this modern era? We can have a security token. So I can prove that I own a car because I have a crypto token that's been signed when I bought the car. And then if I want to transfer it, I can transfer it to you. I put my digital signature onto it. You now own that asset because you have the crypto token related to it. And we're all quite comfortable. Today, I used a token on the bus in Edinburgh to come in. So we're quite happy to use tokens when we travel. So this is a world which is actually starting to create crypto assets. And then we can define how we transfer these, who owns them, and who actually has possession of them. And then at the core of this, as we'll find, is this concept of a private key. The private key is probably your identity. If someone gets your Bitcoin, private key, then say goodbye to your Bitcoins. Once someone has your private key, they can then do what's called sign away things. So it's possible for them to sign with a private key, and then you prove that signing through the public key. So as part of the module, hopefully we'll be trying to understand the complexity or the usage of public key encryption. So what we do in security, it was Bruce Snyer that came up with the concept of Bob and Alice, and we tell stories around them. We have Eve, the adversary, and we have Trent, the trusted entity. Does anybody know any more of the characters that were created by Bruce? There's Malloy is one. C, what do you think C?
Christopher.
Who?
Christopher.
No. Good guess. C is female. Carol. D is male. D, Dave or David. E, of course, is Eve. F, I can't remember. But each of the letters of the alphabet has got an associated person, and when we tell stories around Bob and Alice. So our core story is A and B, Bob and Alice. As a white hat, we must protect them. We must make sure that they communicate and that Bob and Alice can actually identify themselves to each other. So Bob knows Alice and knows that Alice is sending him messages and so on, and vice versa. But unfortunately, we bring in Eve, and Eve can listen to the communications, she can change them, and she can pretend to be Bob, of course. So luckily, we build in trust. Who does Bob and Alice trust on the internet? Probably no one, really, truly. So we bring in trust, and trust is Trent. On the internet, we have trust as in the public key infrastructure. So trust is whoever signs for our digital certificates. Do you know a signer of a certificate? Who would you trust if you looked at a digital certificate? You connect to Google and you kind of click on the certificate. Who would be a trusted entity, do you think?
Root CA, like
Root CA, VeriSign, yeah. GoDaddy, is that one? GoDaddy, yeah. Verizon and companies like that. It's a big money-making scam, if you ask me. $50 to create a key pair? You must be joking. $50, wow. That's a crazy business, that. So do you know who's disrupting that world of having to pay for a key pair? Let's Encrypt, yeah. So you find on my website, I use Let's Encrypt. More malware, more adversarial sites use Let's Encrypt. It's not totally trusted, but it's pretty good and it doesn't cost you anything for the certificates. So we'll hopefully try and understand what Trent means. But could we create a world that doesn't even need Trent? Is it possible for Bob and Alice to trust each other without even needing a trust entity in between? And that's when we look at blockchain and cryptocurrencies, we'll see a world that doesn't need VeriSign anymore. It is a trustless infrastructure with our keys. So I say this, and as you see with the Microsoft vulnerability that the NSA, cryptography and the principles behind it are almost perfect. Okay? They're perfect until somebody finds a flaw in them. Okay? A paper published last week, it's really interesting. Please try and read it if you can. It's called Too Much Crypto. Really interesting paper saying, why do we need this extensive security that takes light years to decrypt when IoT devices are struggling to run some of our methods? Could we reduce the bar and still be secure, but make the performance better? So there's a big balance there. Most of the methods that we have are robust, secure. It's just, unfortunately, that we get involved as humans and we muck up. We do something wrong. But what's the greatest threat to cryptography just now? In the next decade? Yeah, so quantum computers are going to come along. So the methods I'm going to show you for public key encryption are, do you know the methods? Just off the top of your head. RSA. Do you know the other one? Elliptic curve. And since we're in the home of John Napier, discrete logs are the three main methods that we use for public key encryption, and also, as we'll find, for key exchange. And unfortunately, quantum computers can crack each of those methods. Okay, so just watch. If you're encrypting something now with those methods, if your data has to be secure for the next 10 years, then, or 20 years, then there is a risk that quantum computers will come along and someone will be able to unravel all of your data, which is a worry because elliptic curve cryptography is used. Do you know where it's used? Where would you find ECC, elliptic curve cryptography? It's used a bit in digital certificates, a bit as the NSA vulnerability, but where is it? Where is it kind of used more extensively? It's used in blockchain. It's used in cryptocurrency. If you have a Bitcoin ID, you'll find that Bitcoin ID is an elliptic curve key pair derived. So encryption works well until it doesn't. Encryption works great as long as no one makes a mistake. It works great unless something goes wrong, and it works great as long as everything works right. Okay? So don't think, yeah.
So you said elliptic curve is basically dead as soon as quantum computing gets its hands on it, right?
Yeah.
And blockchain is entirely based on elliptic curve encryption.
Yeah.
And all the banks are trying to move all the back office onto blockchain.
Yeah.
So it's a dead end.
So we'll migrate. One thing we've done in this industry is that we've migrated. TLS 1.3 kicks off RSA key exchange. You can't do that anymore. MD5 is history. SHA-1 as a hashing method we're saying goodbye to that. So it's an industry where we've generally taken something and ran with it, and then we've said it's on the naughty step, and it's out. And we've generally done that well. RSA has been around for 40, 50 years. It's kept up, but it's struggling. It's last breath. We're up to 4,000-bit RSA keys, and it's just crazy. So it's an industry that will migrate. And when we look at TLS and SSL, we'll see how we migrate, how we can push things off. I can hire a GPU cluster on Amazon with 8 NVIDIA GPUs for $10 an hour. It does a tera hash per second. A tera hash, that's 1,000 billion hashes. It can go through your password hashes and crunch in 1 second. It will virtually take every single password that you can think of and crack it. So we need to understand that computing power, even in your PlayStation, that GPU is in your PlayStation. Do you know how many processors that NVIDIA card has got? 4,000. There's 4,000 little processors that just love doing hashing and crypto and things like that, and are quite happy to run all in parallel. If you get 4 or 8 or 16 of those, and you don't even need them in your hardware, you can go into the Amazon cloud and you can get 10 hours. Do you know that someone took 3 images? I think it was James Brown, Barry White, and I forget the other image. And within a day, they created the same MD5 hash for each of those images. And so that shows you how credible MD5 is as a hashing method, that somebody can create the same hash for 3 different images. And it's happened now with SHA-1. So someone, I think it was last week or so, someone managed to create 2 documents with the same SHA-1 signature. So now SHA-1 is on the naughty step, and you shouldn't really see SHA-1 anywhere. I appreciate I'm saying lots of acronyms, and I apologise for that, but we will explain the acronyms. The last thing we want you to do is to only understand the acronyms. Unfortunately, in the industry, There are many people, even in senior roles, that would struggle to get past what the acronym actually means. So we don't actually care that much what AES actually is an acronym for. What we're more worried about is how it actually works under the hood. So what will happen is the AES will generally, all the key sizes will get pushed up. So if you use 128-bit AES just now and you're worried about quantum computers, use 256 because it's double 128 times. That's how more secure. So quantum will push the threshold up that 1 bit more. Does that answer your question? you were quite damning in your.
They're just starting to tease it now. We can already see that it's trouble.
Yeah. Our problem is to find a hard problem that computers don't really like doing and make it provable that it's difficult. As we'll find RSA, do you know what method RSA uses to keep security? Takes 2 prime numbers, multiplies them together, and creates what's called a modulus. And computers hate to actually find those 2 prime numbers if they're random. That's the basis. It's quite easy to crack RSA, but because of the sizes of the keys, so about 1,000 bits, NSA could probably crack RSA. Anything more, even they will struggle to do that. On your iPhone, you could probably do 512-bit RSA because you could factorize quite easy. So all of them have a difficulty, and we'll see what that difficulty actually is. So the module itself, the module itself uses a number of tools that we think are relevant for your studies. Probably one of the main things is this one here, Slack. So I don't know if you've used Slack before. It's an amazing tool to communicate, to contact someone directly and ask a question. Email is really difficult to cope with these days. So if possible, we'd like you to go onto the Slack channel. You might have no questions at all, but when you come to the test, then at least there'll be somebody there that can answer you at 10 o'clock on the night before the test or something like that. So we've set up the Slack channel and get onto it just now. Share some content that you find. We can also use Moodle, so you can post your things on Moodle. That's fine. But Slack is a bit more dynamic in getting things set up. So I'll be posting things on Slack. You can use it. If you want to talk one-to-one to your tutor, then there's a bit on Slack that allows you to do that, okay? So don't post answers to tests or something like that. So just watch what you're doing, okay? But I'll send you the link if you've not already added onto it. It's useful if you're away for a while or if you're studying from a distance. The Slack channel will be there. So it's ECQT 2020, which is a cool name, slack.com. We'll get you there. All of the lectures are on YouTube, and if you want to get to sleep, if you can't get to sleep one night, then maybe you can watch the whole lecture back, and that will certainly make you go to sleep. So it's up to you. I wouldn't advise to watch the whole lecture. They're there so that you can go back when we get to the test. The tests are open book. I'll say this again and again and again and again. The tests are open book and mainly written type work. Okay, so I'll give you a good heads up on the tests, what's required, and so on. But we hopefully reduce the stress on you so you can bring your books along and do it like that. If possible, we use Overleaf a great deal. If you move into your dissertation, I highly recommend using LaTeX. and overleaf. There's a bit of a learning process, but it produces beautifully crafted academic work. Things become easier in the end rather than using Word. So for the coursework, we give you the opportunity to use Overleaf. And if you use Overleaf, you can share that with us, and we can have a look at it easier than we can if you send us a Word document and so on. It's just a good technique for sharing in a way that Word doesn't really support that well. Okay, but don't worry, if you don't want to use Overleaf for the coursework, you can use Word if you want. So we'll post things on Twitter, and we have a whole website set up that has all the code and all the examples, and if there's something missing, just say. And finally, and best of all, it's on GitHub. So GitHub is fantastic. It's probably the best thing that I've found from an academic point of view as a teaching tool for a long time. So GitHub allows you to download the whole of the content if you want. We'll be able to update it. If you spot any errors in the notes or the code or anything like that, then we can easily update it from there. So the GitHub is there, and I'll explain a bit more about that later. But everything, that's the source of most of the material is from GitHub. That will then spin off into that website to show some of the demos. Okay? Yep.
About Mac OS, is that
Was it?
lessons in YouTube?
When?
Search for.
I'll send you the links. So on GitHub, there'll be a link that says click here for the lecture. I've got 2 lectures. One I've recorded as a voiceover, which I prefer, and the other will be this lecture, which I prefer less, because it isn't me that's standing in front of the camera. So you can do one or the other. The slides will be there. It's really just up to you which one you prefer from there. But probably it's at the test that you might want to play back the lectures again. Okay? Good. Okay, so hopefully that's not revealing anyone there. Good. That big rectangle doesn't appear there, by the way. That's I added that. So Slack is great. Slack is non-secure, okay? So there you go. A security professor telling you that Slack isn't secure. So watch what you say on Slack, okay? Because anybody can be watching it. But please try to use it. It's great, and it's really dynamic. I can keep track of any questions that you've asked and not miss them. If you send me an email, I don't reply, then please send it again. We get thousands of emails a week, and we just don't want to miss any of them. But it's not that easy sometimes. But Slack, you'll always know if you ask your tutor a question, then you'll get a reply in some way. So I'll try to put, there's weekly meetings. It's probably not so much for the campus-based students, but every Monday at 6:30, there's a WebEx. Just after you've had your something to eat, you could come onto the WebEx, and I'll go through the lecture again, and then I'll take questions, but I'll record that WebEx session so that everybody can actually watch it back again. Sometimes it's great because someone will ask a question that I've not really covered, but I'll make sure that everybody gets an update if I've got new things. Throughout the module, I'll sometimes do like a little 2-minute little demo with a whiteboard if there's something that isn't quite sort of going in from there. So we're going to come across some tough concepts. I can assure you, once you learn them, you'll feel great. Before that, you'll go, oh my goodness, I don't see how RSA works. And then you'll get it, and you go, that's wonderful, I see it. And then you'll forget it, and then you'll learn it again. So that's a good thing. Okay, anybody, any questions about that? Okay, so as I said, the lectures, the lab demos are all on YouTube. If there's something that I've missed off then just say, and I'll record. Maybe there's a bit of the practical bit in the lab that you're not quite saying. I've got no problems in recording it and putting it there. The coursework would be good, and I'll show you how to use Overleaf and LaTeX to write your report. But that's more for the end of the module. And then in between, we've tried to go open. Okay, Windows, we want to go open. We want to be using open source software all the time. So we've tried to create something. We're all about command line, and we're not about GUI at all. So please get into the command line. Please get good at your Linux skills. That's the kind of core of what we're looking at. So the virtual machine we've created is a Ubuntu virtual machine. It should have all the software installed. You can either use vSock to access it, or you can download a VM. I've put it on OneDrive. Some of you have downloaded it already and got it in VMware. I use VMware Fusion on my Mac. From the VMware Academy, you can download Workstation or Fusion. I like it because at least if the network connection goes or I'm traveling, I can still use my VMs. So I'd advise you to download the VM anyway onto your machine and have it there, even if you put it on a USB stick or an SSD drive or something like that. You can get the Ubuntu to work, and it's yours. You can build it up if you want. It has Python installed, Go, and it's got OpenSSL in there. So a lot of the time we'll be using OpenSSL. It's a kind of standard for the crypto. It's almost like a pocket calculator of crypto. If you want to check your crypto, then you run OpenSSL. Something that's taken off massively is a language, if you can even call it a language. Like it or not, JavaScript is pretty much king of the hill in many places just now. It's a horrible programming language, but it's taking off massively. So JavaScript appears in the front end, and now with Node.js, it appears at the back end. So more and more people are writing back-end JavaScript code to implement crypto and security. So some of the labs, and we'll do a little bit of a lab today with Node.js, it's just a JavaScript file that you run through a compiler, and it produces your output in the same way that Python does. So right in the middle there, I've got Python. That vulnerability I talked about with NSA, it was weaponized in one day with a piece of Python code. Python is a standard almost a standard in the industry now. It's almost like your pocket calculator. It allows you to script Amazon instances or Azure, and more industry is using it. So I appreciate you'll be at different levels with your Python, so don't worry too much. We'll give you support if you're struggling a little bit, but Python is where we want to be and develop through that. It's our ways to learn not the language, but the principles behind cryptography will be illustrated best using Python. Okay, so it's important. I still have to look up on the internet when I need to do a loop. I learned C, and I know some languages very well. I use Rust now. It's a kind of C-like programming language. But for Python, a lot of it goes over my head for the syntax. But I still use it mainly, and it's the one that I would go back to if I had to prototype something. The ones I use, Python, Golang, created by Google, produces an executable. So the advantage of Go over Python is that I can produce an executable piece of code that will run on Linux and be... What's the advantage of producing an EXE rather than running Python, do you think? So if I had to choose between Python and Go, say, what would be the advantage of going with Go?
People not see your code.
Yeah, that's a very good answer actually. There's a better answer than that, but that's an excellent answer. Yeah, you got to distribute. You can obfuscate, but yeah, that is a core advantage. Another one. It's so much faster, 10 times faster. To run a script as opposed to run a core exe, it's about 10 times sometimes as fast. So if you're hitting a bottleneck, if you're running it on an IoT device, then you're probably better with an executable piece of code. Okay, so the examples we'll be using are mainly in Python. And if you're interested, I'll put up some Go examples, Golang, in the repository. If you want to try them out, that's in there. And then finally, it's all on GitHub. So I'll show you the site itself on GitHub. So this is the code. They call it the chain of fools. The chain of fools is the NSA announced vulnerability. You actually see it's a Python code. I appreciate that it'll look gobbledygook to you just now, but hopefully by the end of the module you'll be understanding a bit more about some of the difficulties. It took one day for somebody to... It's funny that people were asking me, should I patch or not, because it's not been weaponized. Go, yeah, patch. Because somebody somewhere will just create a little Python script and it'll be weaponized in a day. I mean, you're talking about hours now between announcement and weaponization. That's how quickly it takes. The community is fast to take a vulnerability and weaponize it. Okay, so this is the main GitHub here. So you'll find that this introduction is here. So this is the introduction I'm giving just now. If you click here, you'll get the YouTube video. And this is a demo of me using the Ubuntu machine. And if you want to download the VM, you should be able to click in there. Okay, so I've got the timetable there. So if you want to book your flights and so on, you know when we'll be doing our test. And that'll be in week 9 and week 14. Okay, we won't change that. Please tell us early if there's a problem with those dates, and we'll try to move. But as we get closer to them, they're pretty much locked down. But just say if there's a problem. Okay, so you find the PowerPoint and the PDF is there for you to have a look at. And for the unit that's coming up, that's Unit 1, you'll find that there's things, questions, and so on that you can actually start to look at. We'll give you the basic learning outcomes for the unit. But each week there'll be a lab. So today we'll have our lab. Go into the lab, and you should find the most up-to-date lab is in there. Okay, so we'll do that a little bit later. And if you have any questions, then just get on Slack. If you're not in the lab, please ask. These are some of the answers that are in there. Okay, we've got an associated site called our security site, and you'll find that content is pretty much replicated there, but there'll be more in-depth details. You can have a look at the test guides. Don't be too worried just now. By the time we get to the test, you'll actually know what it actually means. So like when you look at the test guide, you go, oh my goodness. But really, when we get to it, you'll actually understand some of the things. So it's very much an MSc type test, quite kind of academic, and it's there's no multiple choice or anything like that. You'll be asked what's public key encryption, and Bob passes a public key to Alice. Describe, explain, critically appraise some of the security problems. There's probably no right answer. we're looking for you to build up your own critique and your own answers. So don't worry that we're always looking for this is the right answer. There are many ways to say, well, this is good and this is bad, and so on. Okay? So that's what we'll do. And as I said, it's an open book.
Information is not available in the model.
Say again?
This information available in the model as well.
In Moodle, yeah. So there'll be a link on there. I'll replicate it from there, but you'll find the GitHub will be it'll be formatted in the right format that we want. So it'll be replicated here on GitHub and also in Moodle. Any other questions? Good. Right. So that's that. In terms of the timetable, so this is the timetable that we're looking at. We'll try and run almost exactly to this. So this is week 1, and we know it'll take a few weeks for everybody to get up to speed and so on. So just take your time and ask questions. And if you're struggling with anything, then please ask now from there. So next week is our first proper unit. I'll give you a quick introduction to ciphers and things like that if you're interested. But next week will be our first real unit and looking at AES encryption using symmetric key. Then on to hashing, public key encryption, key exchange. We'll have a guest lecture in between, on to digital certificates, tunneling, and then our first test will assess the first 5 units and there. So that test leads on to there. Then we'll have our second test. You'll get feedback, see how you're getting on, what you could do better, what you're doing well, and so on. And it's worth 25% of the whole module. So it's not a lot, but it's enough to be still significant from there. So even if you crash it, then it's okay, you've still got 75% of the marks. You learn, and then the next test is really focusing on the next units from there, and that's again worth 25%. And then in the end, we have a coursework for 50%. The overall pass mark for the module is 50%. You don't have to pass all elements, but you have to get an overall 50% as a grade. Okay? If you're still struggling at the end of test 2, we'll make sure your coursework is really great and gets your mark back up. Okay? Any questions on that at all? Good. Okay. So how does this all fit together? So I've tried to encapsulate it really as what happens. So please try and, whenever you see that little green padlock when you connect to Google, kind of think, what is happening here? How's this being created, and what is a certificate, and how is it being used, and what's the encryption that's involved, and how do I know if that's even secure? If I connect to my VPN for my company, question what's going on underneath. Don't just take it for granted that somebody has made all this secure and everything's fine. So with encryption, what we have is that we have the core around the symmetric key encryption methods. Those are the workhorses of the industry. AES is the premium symmetric key method. NIST standardized it, and it is used, it is fast, it is efficient. Unfortunately, it's not that efficient for IoT. So if I'm a little sensor on a device and I'm using AES, I'm really going to struggle for memory, for processing power, and so on. So luckily, there's new methods called lightweight crypto that we'll have a look at that are much more efficient when it comes to using limited devices. Cha-Cha-20 is another one. It's what's called a stream cipher. Streams are so much faster than what are called block ciphers. AES is a block cipher, needs a lot of memory and so on. Stream ciphers like Cha-Cha-20, probably when you're connecting to Google, you're not using the AES, you're using Cha-Cha-20 because it's much more faster and efficient. So we create a key, we create our tunnel, and we create our encryption. But how do we get the key? How do we get the key? And how does Bob and Alice get the key so that Eve doesn't know it? Eve is listening to it. So we have magical methods that allow Bob and Alice to openly communicate, and they both end up with the same shared key, and nobody can actually find out them. At the most extreme, we have end-to-end encryption, which scares many governments and people. And I think Australia is looking to put a backdoor. So I don't know if you can find a backdoor that works for the good guys and not for the bad guys. I don't think that really exists, like a magic wand. I'm good. There's my backdoor, and then the bad guys don't find out about it. So it's not an easy thing. So with end-to-end encryption, we tried to make sure that from Bob to Alice, we get a complete encryption tunnel, because most of the encryption that we have is from machine to machine. So TLS takes you from one machine to another. Somebody installs a proxy on your machine, and they break the tunnel. So if you record traffic through a proxy, someone puts a proxy on your machine, that's non-encrypted. So more and more we need to move towards a complete end-to-end encryption so that only Bob and Alice know that every single time the key is different. And even if I do find out their long-term key, I can't go back and look at all the previous keys that they've used and decrypt them. So that's the methods. Diffie-Hellman, elliptic curve Diffie-Hellman. We'll be looking at those methods. Those are the methods that are used by your browser when it's connecting to a secure website. And then we need some way to make sure that the data that we're sending or receiving is that data. So hashing methods gives us our fingerprint of our data. So as I said, MD5 is one. It's on the northeast, definitely on the northeast step. SHA-1 is likely to leave sometime soon. So we probably start at SHA-256 for our hashing methods. We also have what's called a MAC, a message authentication code. It's where we can get a hash and we can sign that with some shared key that we have between Bob and Alice to make sure that they can sign the message. And then we use public key. We use these key pairs. Bob signs something with his private key, and then Alice proves that with Bob's public key. So how does she get the public key? Well, luckily, we have Trent. Trent signs the public key so that Alice knows that that is a true public key for Bob. And then we end up, this becomes a trust authority and looks after the keys for us. A large bank will have hundreds of thousands of key pairs. One of those key pairs, if they were released, can cause a major problem for security. And then in the future, we'll be using new techniques. Why do I have to give away my password every single time? Why can't I just prove that I know my password? I've proven to you once I know my password. Give me a puzzle to prove that I still know it, and then I'll solve it for you. So with zero-knowledge proofs, we actually don't have to give away our information. We can actually prove that something is correct without us actually revealing the original information. So later on, we'll have a look at zero-knowledge proof, and then we'll also have a look at what's called homomorphic encryption. It's a scary thing that we can actually process encrypted values. So we can actually encrypt all our values, and we can still mathematically work on them. So you could have a spreadsheet with encrypted values for all the fields, and then it would calculate the total as an encrypted value. We're just on the cusp of having the computing power to be able, you would need an IBM Z series computer just now to run homomorphic encryption at scale, but it's getting better and better all the time. And within probably the next 5 years, you'll see homomorphic encryption being used. And that way, a company could actually encrypt all the data and not actually reveal it, but still be able to process on it. And then there's a whole lot of other things that we need to look at as part of the module. Okay, so that's the areas that we're going to look at, next for our basic fundamentals. Then next week, we'll look at symmetric key encryption, looking at what are called salting. It's a very important method that we have to make sure that every time we cipher, we change it in some way, because we don't want somebody to copy and paste our ciphers together. So we salt. And salt's really important when it comes to hashing your passwords, to make sure that your hash will always change. So rainbow tables are finished, if you know rainbow tables. They take a whole lot of words and so on and produce a hash. They've kind of gone because most of the hashing that we do now is with a salt. So you need the salt. So most of the cracking that we do is with Hashcat. And the unfortunate thing, the salt is stored beside the hash value. So it's not that difficult to take your dictionary and recompute again with a hash value, especially if you're using these GPU clusters with 1 tera hashes per second. It's not too difficult to reprocess that again. So have a look at salting and what salting actually does, and then we'll take a deeper dive into how AES works, Chapter 20, and then finally, you might think you've got 256-bit security and that you would need all the energy in the whole of the planet to crack one cipher, but actually you're using QWERTY123 to create that key. And that's what's called key entropy. You think it's fantastic, it's got excellent security, but actually you're only using 1,024 words, which only gives you about 10 bits of security. And so key entropy measures how secure. We'll come up with a value of 72 bits here. 72 bits is probably the threshold of cracking just now for symmetric key encryption. Anything more, it's double, and so on. So 128 is a good headroom between us, but every year we lose a bit because computing power gets better and so on. Okay, and then we'll look at hashing methods. In the lab, we'll especially be using Hashcat there. And Hashcat will allow us to get the salt and the hash value, and then hopefully find out the original unhashed value from there. So we'll look at the core methods, and these are fast and these are slow. And we'll find that these ones are really good because they're tortoises. These are hares, and that's not good because if we've got a 1 tera hash, if we've got a 1 tera hasher per second for these guys will only be maybe 100 hashes per second. So if someone gets our bcrypt, then it's going to cost them a lot of money on Amazon to just try a few different values. So we'll find these ones are good, bcrypt and PBKDFS2. That's what Wi-Fi is using, that one, and the bcrypt is used quite often, but we'll also have a look at the other hashing methods. Okay, well, so along with that, we'll look at how we hash our passwords and the different ways to do that. Look at every single method, and we'll write our Python code just to be able to run through all of those methods. Timed passwords are used extensively, so you probably find when Anybody use multi-factor authentication now? I use it all the time. Yeah. So I've got my mobile phone. I didn't lose my mobile phone. I just lost my SIM card. I don't know. It dropped somewhere while I was there. It's evaporated. Don't know where it gone. And then, but I use my mobile phone for GitHub. Most of the apps that I've got now, I'll get my little code on my app. I'll put my code in for AWS and things like that. I highly recommend it. So we'll have a look at how timed one-time passwords are created and how you can actually lock down either as a sequence that you go through or as a timed. And then finally we'll look at message authentication codes or MACs. And then we'll look at public key encryption or asymmetric. Symmetric, one key, asymmetric, two keys, public key, private key. So we'll be taking a deep dive into RSA and trying to understand. We won't go into the complex mathematics of the proof and so on, but we will be looking at the basics of how it works from there. Then into elliptic curve and how that works. A lot of my work is around elliptic curves, and they are becoming more important in terms of IoT and blockchain. Everything that's created now with public key kind of has elliptic curve in it, and RSA is just hanging on from them. And then we'll have a look at PGP. I appreciate PGP, not many people use it, but it's a good example of how you can use, how you can create trusted signing and so on. Then key exchange, look at the basics of the Diffie-Hellman method. Then going on to elliptic curve Diffie-Hellman, which is used most often when you connect to a secure website. Then the wonderful world of digital certificates. Yeah, that's a nightmare area, and one of the least understood in the whole of the industry. I hate to say it. We really need to understand what it is about certificates that are so difficult. They're not really difficult, but we need to understand the whole of the trust infrastructure that's created by them, how we can sign them, and how we can create signatures from them. Then tunneling, we want to look at SSL in the detail about what SSL does, and look at the Wireshark traces and see what the communication is happening. If we're using weak crypto, there's a site that rates your site A to F. If you get an F for your site, then you're doing something wrong. And many sites do get an F. So we'll have a look to see what happens in there and how we create that contract, and then on to IPsec, which is a much better way to actually create our tunnels. Then we go into the future, into blockchain and cryptocurrency, and we'll actually run Ethereum. We might even run Hyperledger if we've got time and resources. We use Hyperledger most often. It creates what's called a permissioned blockchain, in that only people in that community can actually see what's going on. We don't quite like the public blockchains like Ethereum and Bitcoin, because everybody can see what you're doing. We're using much more private and permissioned blockchains. So we're very lucky. We might even, I'll give you a demo of Hyperledger at least, but a lot of our work is now on that. So we'll have a look at things like smart contracts and how you can create these systems. Then we'll look to the future and over the hill of where we are now. As graduates, you need to be understanding where the industry is going and show a vision of the future and show your migration paths. So zero knowledge proof, homomorphic encryption, lightweight crypto, and quantum robust. We'll kind of touch on them a little bit, but we'd like you to investigate them as part of your coursework. So you'll be given the chance at the end of the module to pick off your favourite subject and then maybe dive in a bit more. It's like a little prep for your dissertation. It's like a mini dissertation that you'll do find some GitHub code on a lightweight crypto method, run it, see how it gets on, do a bit of a lit review. That's what we want for your coursework. Okay, and that's the main modules. Does anybody have any questions on those things? It seems a lot, but...
Could you just repeat that last little bit? So, future crypto, Lego cryptos, code robust stuff, something that's what we're going to focus on for your project.
At the very end, for the coursework.
So you said project code or something?
Yeah, so for the coursework, it's a bit of research. You do a little bit of a lit review around post-quantum crypto. You find some Python code from a GitHub, run it, do a basic benchmark, and write it up as a little mini paper. That's what we'd like you to do. But there are other areas, and if you find your own wacky area, then you can propose that. These are just examples. If you're really interested in building your own quantum computer, and you can't do it. Somebody gave a demo of it with a Raspberry Pi. I don't know the details. Somebody said you could build a quantum computer in your house or something like that. If you wanted to do that, then that would be fine. As long as it's academically challenging a bit. Blockchain is another one, and crypto. If you wanted to build your own hyperledger, we can show you how to do that and get it all set up. You don't have to get into the guts and build a big app or something like that. We just investigate the method. Does that make sense? A bit, good. It's on the GitHub. You can have a look at the coursework spec, but we'll have lots of opportunities to discuss later on. Does anybody else have any burning questions at all? Good. Right, we'll have a break for 5 minutes, and then I'll give you a quick run through ciphers and some of the fundamentals, and then we'll do a little test and at the end of it. Okay, thank you. What's in this unit isn't actually in the test. Okay, so it's a very very basic introduction that you can go and watch the YouTube video and maybe go through the whole lecture. If you're interested in ciphers, traditional ciphers, then have a look at the video. Ciphers are finished. We don't do ciphers anymore. We don't do that traditional Caesar cipher and so on. So we do cryptography now. But this is just a little, if you're interested in doing ciphers, we've got little tests for you to do to get your brain into gear. One thing I know about this subject and this area is that detail matters. Developing your eye to be able to spot things, to get things correct and to be precise is better than being fast. Okay, so take your time, do things correctly, and don't do things with haste. If you do things with haste, you'll muck up. You just need one bit to be wrong, one single bit, and you could rip apart the whole security of the world, basically. So just watch what you're doing. But I want to have some time for a little test. We'll do a little test every week, a little fun test. So I want to have a little bit of time at the end for that and to find out a few things about you. So I'll cut this lecture kind of short, and then we'll go to the test for that, if that's okay. Okay, so you've seen that already. We're all about Bob and Alice. Unfortunately, Eve exists, and sometimes we are Eve. There you go. We got to think like Eve. Sometimes we are Eve, and so on. So we're either there for Bob and Alice, or we're there for Eve. And sometimes we're Trents and them. Okay, the core of this whole module was kind of created in the 1970s. Sounds kind of old now, but my goodness, these people actually set things up that have got things going. So a lot of what we're doing was kind of built by these people here. Here we'll start. These Revest, Shamir, and Alderman created RSA from their names, and it's still around. They created public encryption. It was this person here that he proposed public encryption, says that it could work, and they went along and actually did it. Actually, it was created in the UK, but don't tell anybody. It was created in GCHQ, but it was kept secret. At the same time, Ravesh, Shamir and Alderman created their things and published it, but it was people in GCHQ in the UK that actually was the first to propose public key encryption. Whitfield-Diffie, part of Diffie-Hellman method, proposed a key exchange, and we're still using it now. We'd love to get Whitfield-Diffie over to Edinburgh. Luckily, we had Bruce here last year. Wow, I stood on the same stage as Bruce. Bruce got me into this whole area. So I read his book, Secret and Lies, and it completely changed my whole viewpoint on the world. He showed me a new world, and I could believe that was the world that was evolving. So please subscribe to Bruce's blog. Go and read some of his books. Inspirational person from there. So that's Bruce. I rate him number one in the whole of the industry. He's a person, and he's not a big corporation. And I respect people's ideas as much as I do corporate ideas. Then Ron went on to be a professor, and he created MD5, MD4, and other methods in them. And then Phil Zinnemann came along and said, why is email so insecure and so rubbish? Why can't I sign it, and so that when you receive the email, you can tell it was from me and hasn't been read by anybody else, or it hasn't been changed? So he came up with pretty good privacy, PGP, and he proposed a model. He nearly went to prison because of it, because of export. This is seen as in the same vein as nuclear weapons. Cryptography is something that the good people use, but also that bad people use. So he nearly went to prison. He sourced his code outside the US, and you'll find there are GitHubs in Switzerland and so on that are there for a reason, because of the export munitions laws. And he's still in there, still a great person to read. These two people actually created AES. It was called Raindial at one time. NIST had a competition, and Raindial actually won, and it became AES. Any idea where they're from? Which country?
UK?
Yeah, good guess. Dutch. Sounds like they sound Dutch, but no. Belgium. There you go. Yeah, that fine crypto country, Belgium. They're from Belgium. And they created Raindial, which became AES encryption. Okay, so ciphers have been around for a long time. Love and war. We need to keep things secret. In a war, that's what we need to do. And we have many different examples. In this case, it was the Navajo Native Americans. Language was used in the Second World War, and I don't think it was ever cracked. It was such a difficult language that you could almost, it was almost uncrackable in the ciphers that was actually used in. So with a cipher, what we typically do is we encode something, and then we decode it, send it over a channel, and as long as Eve doesn't know what the encoding and the decoding is, the secret, then everything is going to be secure. Unfortunately, once Eve does know what the method is, then our cipher is then cracked. So there's been many ciphers and many encoding methods that we've used in the past. So this is Morse code, and this is an interesting one here. Can anybody work out that one? It's a T-shirt you can buy online if you want to buy it. I was going to get one. I've got ones that have got Morse codes. We get that one. Developing a good eye is good in these things. First letter? N. Second? What was it? No. Second letter? U. Yeah. Next one? F, yeah. I know it's not spelling a word. It doesn't spell a word. C. Anyone know what that stands for? That's Newcastle United Football Club. So if you've ever seen a Newcastle United match, you know that like the whole stadium is black and white. I wouldn't recommend you going along with that T-shirt. This says "I love you" actually. So if you've got somebody that you adore so much, they'll probably divorce you straight away. That's in Morse code. Look at it. So Morse code is one. It's an encoding method. Okay, it's an encoding method that everybody knows about. And so use things like grids. So in this case, 2, 3. If you know the grid, you can actually work out the code, and that was used by the Greeks there. And then you get the visual ones. I've missed off that in there. So without me even telling you, can you work out what that cipher is there? I won't tell you how to do it. And I mean, this is the core skill in cybersecurity, is that ability to see something completely new. And Napier, that's right. So it's a N, so that's that. It's an A, that, and a P is that, and that one is there, and so on. Does everybody see it now? Yep. So the good thing with that, it's a graphical one, and you can, and it's actually the Masons used it as a headstone of someone there, and it was used as what's called the Freemason cipher in them. And you've got other ones that are based on grids that we can actually set up. And then the Playfair code was one of the few which used a key. So in this case, we use a key of Napier Uni. Okay, we don't repeat the letters, and we lay out our grid like that. So in this case, Bob and Alice share Napier Uni as the key. They then lay out the grid without repeating the letters, and then lay the letters back again to be just the grid. We then take 2 letters at a time. We take our grid, and there's the letters there, and we take the letters that are opposite as the cipher. And it's quite a difficult cipher to crack, but obviously once you have the method, you can work out what the code is. Luckily, Python is there, so if you need to ever crack it, then there's always Python code that you can get. And one of the most basic ciphers that we did all at school was to shift the alphabet. I always remember getting this at school, and God, this is amazing. That's probably the only thing at school that I can remember that I really loved, because I could send secret messages and so on. I think I've never lost that. If you've lost it, then please try and pick that child like innocence of loving secret messages and so on. So we shift here. So can anybody crack that? Normally with ciphers, we have uppercase for the cipher and lowercase for the plain text. We define that as plain text and ciphertext. Can anybody crack that one? What is it? Yeah, hello, yeah. What is it? No. It's hello, okay? So that's H. How many ciphers are possible? Is this a secure? We've found good cipher here? Is this good? No. How many are possible? 25, possibly, because obviously one is just the same as... I wouldn't recommend you use the 26 shifts. It doesn't actually work. But unbelievably, he used a cipher. He didn't want to use things like AES encryption and so on. So he stored his secret data in spreadsheets with a simple Caesar code, and the police couldn't understand what the codes were. No, it's not AES. It's not this. Oh, well, why don't you try a Caesar code? And they actually managed to crack it. So a better one is to use a scrambled alphabet in there. So we just scramble the letters in there. Can anybody work out that cipher? Plain text for that cipher? Just shout out the letters. First letter?
Inkwell.
Inkwell. Okay, Inkwell. And there. You see that? So is this secure? How many different ciphers? There's actually that many. Okay, 26 factorial. For the first letter, we have 26 choices. And then we have 25, 24, and so on. So that is that many. Even if you have your GPU Amazon cluster, in fact, take over the whole of the Amazon cloud, you're not going to do that very quickly from there. So it looks like it's a fairly secure cipher, you think? Yep, looking good. So tell me how I would crack that. Give you a clue. Scrabble.
Common letter.
Yeah. So E is the most common letter by far in the English text. So it's something like this. G looks to be very popular there. If we do a frequency analysis of this, then we could map G to an E and so on. And this is the common sort of factors here. We also get digrams, trigrams, and words themselves. We could probably pick off the from here, and there's the again, and so on. So as humans, we are really good at this type of things. So if you want, I've got a 5-minute challenge for you. It's not in the test, so don't worry. On the website, go and do a little scrambled alphabet. See if you can do it in 5 minutes. That's the kind of benchmark that you could do. And I'm not going to tell you what the method is. Come up with your own method, how it fits in your head. Okay, so I've got a little analyzer online that you can feed in some encoded text, and then it will give you the frequency analysis of it. And it does a very quick mapping to what would be expected. E, then T, A, O, I, N, S are the sequence of the most popular letters. I then do a quick mapping here, and it's not too difficult, hopefully, for you to crack that cipher. So the Visionaire cipher is one that uses a key. So we use a key of green here, and what we do is that we move the key from a G to an R, then to an E, and then we do our mapping just as we would with our codes. So you can see that H with a key of G moves to an N, and then we just keep going through like that, and from there. Unfortunately, if you have enough Visionaire, you can do a frequency analysis, and you can start to pick off the length of the key, and then from there you can actually crack the cipher. So I've got a little example online if you want to have a look at it with a Python code, but it's not too difficult to break the Visionaire cipher from them. The ultimate is what's called a one-time pad. And we come up, Bob and Alice agree to what the pad's going to look like. They then cipher their message from the pad and then can actually pass it. The biggest problem with this is that the pad is finished and you've got to create another one from there. So this is the most secure cipher that you can ever get, but you can only use it once from there. And then we can use what's called a frequency analysis type code. In this case, we have lots of different codes for the E, but for Z, we have very few. When the actual the cipher appears, when you do frequency analysis of it, it looks like that everything is appearing in the same frequency, so you can't actually work out what the most probable letters are. Okay, so through the module, we'll be using hex and base 64 fairly extensively. That allows us to convert from our world of letters into a binary form that computers understand, and we need to represent them back into a human way. So if we have characters that are non-printable, we need some way to represent them, and we normally represent them in hex or base 64. I could tell you the key was 011105000101, and you're not going to remember that, but if I can tell you my key is XIDMGQ, then at least you can actually write that down. So those are the two main methods. With hex, we take our bit stream. We normally think of either a bit stream or a byte array. A byte array has a whole 8 bits in each of the elements of that byte array. With hex, we take 4 bits at a time. As long as we can count up to 15, we represent the bit value as our hex value, and we convert it into hex. And base 64 is what's used extensively in sending binary information over the internet. We take 6 bits at a time, we convert them into a number, and then that number becomes our character. We have 4 multiples of 4 characters with base 64. If they don't have enough characters, we pad with an equals. If we don't have enough bits at the end, we put zeros at the end of our last value and then convert that in there. So you can normally spot base 64 because it's got a couple of equals or 1 equals. Sometimes it doesn't have any equals at the end, but it should always be multiples of 4 characters at a time. Would like you to be able to do this manually, to take a character, a string, convert into bits and then into base 64, but we won't ask that in the test. Okay, we keep things really simple in crypto, and we use very simple operations. 2 operations that we use are rotate left and right for our bits. That's a kind of scrambling process. If I move them to rotate by 2 places, I can reverse that by doing reverse 2 places the other way. Okay, so you'll find that symmetric encryption just does that, just does those operations, and then on the other side it does the reverse. The core operation that we often use is what's called exclusive OR. And XOR is like a little adder. 0 and 0 gives you 0. 0 and 1, 1. 1 and 0, 1, 1. And 1 and 1, 1 and 1, 0. Yeah, forget carries. So we don't carry in this module. Okay, no carries. It's a 0. Okay. So that's the operation. The great thing about XOR, do it once and then do it again and you get back your original. XOR is amazing because you can XOR your bit stream with something and XOR it again and you'll get the original content back again. So those are the core ones that we use. We'll also be using mods. And in mod, does everybody know what the Python operator for mod is? Little character. It's a %. Okay? 5 mod 3 is 2. Okay. We're not interested in the actual divide. All we're interested in is the remainder. Okay? Nothing else. So we use the mod for this operation, and it gives us the remainder. And that's the main thing that we're actually interested in crypto. We also represent our characters in many different ways. And we've got to find, in Python, we've got to find ways to show bit patterns and characters and so on. So there's some of the ways: 8-bit ASCII, 16-bit ASCII, octal, hex, characters, stuff like that. So we need to understand that we represent our bit patterns in lots of different ways, and that we get non-printing characters. Try to remember 13, because it's there, you just don't see it. And 10, 7 is there, it's a tab, and backspaces, and a space is a 20 hex. Okay, that's really important because you don't see it, but it's still there as a bit pattern. Okay, you'll find later on the module, we'll be looking at ways that we can make it difficult for computers to crack things. Two difficult puzzles are when you've got lots of keys and it has to search through every single one to find the right key. And the other puzzle is to give it a bit of maths that it really doesn't like to do. So it doesn't like to factorize a big number like that. Okay, so we'll be taking prime numbers and multiplying them together and getting a value. And we need to, these are prime numbers, and we need to be able to find the two prime numbers that created the original. Okay, so a lot of public keys involving the mod operation and prime numbers. Another little thing that we'll look at is what's called the greatest common denominator. The greatest common denominator is the largest value that can divide into two numbers. In this case, what's the greatest common denominator between 12 and 30? 6. Well done. In most cases, we're interested in actually just finding that there is no common factors between two numbers from there. But again, in Python, we can create a little bit of code, takes 2 or 3 lines, and we can create that little method for us. The other thing we do in crypto is that most software stops here, but we keep going right up and well beyond that. So we create what are called big ints, and these are massive, massive numbers, and you can't do the normal mathematics on them. So a typical size might be 2048. That's what a 2048-bit number looks like, and the processors will hate that with their dinky little 64-bit registers. So you find that Python represents them as a string. Actually, they're all just strings, and then the big ints get converted. The thing I love about Python is that I don't have to create a new object, big int method thing. Python just knows that I'm dealing with a big int. It says, that's fine, I'll deal with it. You just do whatever you want, don't bother. But in other languages like Java, you've got to do your big int and all that kind of methods and objects and stuff like that. Python calls it, but it will fall over. There are limits to Python. It will give you the wrong answer. So just watch when that happens. But I'll explain a bit more. And then finally, we've got random numbers. Oh my goodness, that's a disaster area in itself. You've got real random numbers. Anybody know what a real random number source is?
It takes you to do something.
That's it, yeah. Keystrokes and mouse movements and things like that. The electrical noise that you get from a circuit, things like that, are real random. And if you need to get a real random, you plug in a module that does that. Most of what we have is pseudo-random. Pseudo-random is that I can predict from knowing the seed that you've used exactly the random sequence. But tell developers that sometimes, that I can guess. If I know your seed, I know exactly what random number you're going to come up with, and you'll find they'll look with a blank stare. So just watch your random numbers. If they're not random, then you're generating something that can be predicted. Okay, so that's what we're going to be looking at. We'll look at key encryption and how we use that. Look at private symmetric key, public key, and hashing methods, and try and understand how they all actually fit together. One of the most important things is that the size of the key matters greatly. The more keys that we have, the more difficult it becomes. The limit here is 2 to the power of 72, 72 bits. That's the number of keys. That's probably the limits of the cloud just now to crack a key within a reasonable time limit. But every year it gets faster and faster and we move on. But the total number of keys that you have is 2 to the power of n, where n is the number of bits that we actually have. Okay, so I've given a very quick, brief walk through. What we'll do now is a little test. So if you get your phones out, I don't know how long we've got for this, but we'll give it a try anyway. I'll try and keep some time each week for us to have our little quiz. Okay, so if you just go to menti.com and put in that code. I'll try and bring along a prize every week. So whoever wins this will get a prize. Okay, not be a very good prize, but there'll be a prize. That's it. There we go. Oh, there we go. Can we have a cat? Can we have a cat? Okay, so get yourself connected, and we'll do a little test every week, and I'll bring a prize along. Maybe I'll do a really good prize at the very end. Okay, mostly connected then. Everybody signed the register too. Right then, 4391. There we go. Okay, just tell me what iOS. Let's see if anybody has a Windows mobile there. Okay, I like to know the balance between Apple, iOS, and Android. Interesting. Oh, kind of got 50-50. Obviously a very rich audience here. Nobody with a BlackBerry, nobody with Windows that wants to tell the world. You shall be saved. Okay, so we're all mainly there's twice as many Androids as. So I've got an Android, but I've got an iPad, and I'm all mixed up. I kind of want an iPhone too, because it all kind of works together. But that's fine. The crypto's really good. Okay, this is a proper TPM chip. It has a secure enclave, actually, and the way that Apple looks after the crypto is pretty good. Okay, so don't dismiss Apple's methodology. They are fighting against end-to-end encryption and so on. So doing quite a good job. Oh, there we go. That's it. Anybody else? That's right. I know it's a slow phone you've got, is it? Who was that one? Okay. The answer to this one is probably none of these. But which one of these subjects do you think you're looking forward to? There we go. Oh, yeah, tunneling is looking good. Docker. Oh, we're going to do Docker. Yeah. Docker's looking good. Blockchain's looking good. Tunneling. Excellent. Good for future. Oh, that one got kicked off there. Whoa, yeah, someone's went for AES encryption. That's good. Yeah. There'll be one person at the lecture next week, so that. Okay. Oh, poor old key exchange. No, I know. No one's. Key exchange is pretty good, honestly. You'll love Diffie-Hellman method, and we're in the home of John Napier, so it's all discrete logs and stuff like that. So, and hashing, you'll adore hashing, honestly. Once we do Hashcat in the lab and you understand salt and stuff like that, it'll be fine. So a lot of crypto geeks in the audience there. A lot of kind of future Docker. Oh dear, poor old little digital certificates. I'm going to make the whole module in digital certificates. Okay, that's fine. So that's good. A little bit of host security. That's good from them. So how many characters do you have in your main password? Be honest. I'm not tracking anybody here. Roughly, you don't know that humans can only do about 10, and then we kind of lose it at the end with something. We're not that great. We have a short-term memory that's really quite small from there. Oh, more than 11. Who has more than 11? Who is it? You're going to admit? What's your password? QWERTY, 1, 2, 3, 4, 5, 6, 7. Okay. Oh, I'm worried. I'm worried a little bit. But good, nobody has a password of 7. You do know that 10 is finished. Anything below 10 is easily cracked by, I'll show it, by GPU. 10 is finished. No matter, and it's finished anyway with more than that, as we'll probably see. Okay, for two-factor authentication, are you using multi-factor for most of your logins, or do you not use it any? Excellent. Very good. Very good. Good. Oh, there. Just hide that one away.
What do you mean by two-factor?
You'll get like you'll get a message on your phone to say put this code in. Highly, I can't underline enough how good that is. I know if you lose your phone, you think that it's all going to fall apart, but there is ways around it and things like that. Oh, that's not too bad. Not too bad. Okay, in the past, have you used your favourite football team, your family pet, someone in your family? I think someone in your family is going to be the top one here. No, that's a bit worried. And a place there. Yeah, good. Someone in your family. Okay, good. Someone in your family. No football. No Liverpool, 1, 2, 3. Manchester, Arsenal, Spurs. You looked a bit. Oh yeah, you got my password there. Okay, so places that were important to Edinburgh, Glasgow, Barcelona. Yeah, interesting. Usually it's someone in your family. Okay, if asked to do an uppercase, let me think. I'm not even looking at the screen. I think you put it at the start. Oh, no, that's good. It's good, a bit of tension there. You do know that Hashcat knows that and has a pre-prepped rule that basically just takes a dictionary and all it does is move the first character. Oh my goodness, 16. Oh, put it at the end. What crazy person puts it at the end? That is a rule too, you know that. Who does that? Go and tell me. It's you. You do. Tell me why you do that.
Because if it doesn't ask me to do it, I won't think
But you always put it at the end, do you?
Yeah.
Yeah? Okay. So everybody knows that now about you. and that's fine. So, and place it randomly. What crazy person does that? What could you? Oh, you're going to get a first class in this module. I know that. I know you are. Okay, how many uppercase letters? I think the answer is 1. Oh, 1. Oh, 2. Oh, there's a bit of attention there. Oh, there we go. Come on. 3. Okay, Hashcat knows that. Okay, Hashcat knows that you're only going to use, it doesn't have to go through all the uppercase, lowercase. It just does 1 at the start, normally. And nobody has more than 3. If they have more than 3, that's all uppercase. That's what they are. Okay, if you put a number. Okay, I'm not going to look at this. I think you put it at the end. Come on. You can be honest. Go on. Go on. Keep. Oh, is it you? Do you? You're upside down. You know that. You're all back to front. You're back to front. Okay. Right. But there's something in the middle. But I kind of know what you're doing here, and I think I know what you're doing. So how many passwords do you have? I'm going to admit here, well, maybe I shouldn't. As a crypto professor, you can maybe guess that I have 1 million passwords, but that's not the case at all. Not too bad. Who has more than 10 passwords? And you remember them all? Yeah? Well, all of them, are you sure? for every site. Oh, you're using a password manager. Okay, well, most of us have only got a couple, and some people have only got one. I've kind of got two that I kind of dance around, but unfortunately that's recorded, so that's okay. And when asked for a new password, do you just reset and it's all new and everything's fantastic, or is it kind of the same as what you did the last time? And you just hate when they say you've used that 10 years ago and you can't use it. Oh, God, my brain's going to melt. I can't remember more than 3 passwords. Oh, not too bad. I bet you change it completely. There we go. He thinks in hex. He dreams in binary. Okay. Right then. So I think I've caught you out here. Has anybody ever done that in the past? Oh, you do know that Hashcat knows that, okay? Hashcat has a lovely rule that changes E's to a 3. It does change an A to an at, okay? It'll take the dictionary and it'll find the A's and it'll just change that to an at. Hashcat decimates the space completely because we're all sheep. We all just follow. So who wants to admit? Do you want to admit to using one of them? No? But you do it. No? Uppercase. All uppercase. Anybody want to admit to one of the rules? No, of course you shouldn't admit to rules. That, I have used all of these in the past, by the way. But Hashcat knows that, and we'll see that when we look at our rules. Okay, don't swear. Give yourself a little name, and we'll have a little quiz now. Okay. Okay. The faster you do it, the more points you get. It's a bit of fun this week, but I'll bring along a prize maybe next week. Oh, who's that? Who's that? Who's the ghosty thing? But, I think I've had too much to drink the night before for that one. Right then, so you get more points the faster you can do it, but you obviously... so I didn't quite tell you about this, but in the LinkedIn and the Yahoo hack, what was the most popular password, do you think? Given a default password, what will most users go for? Eh? And they're really smart, these users. What do you think they put in? 2 million people selected 1, 2, 3, 4, 5, 6. Closely followed by 1, 2, 3, 4, 5, 6, 7, and 8. Password 1, 2, 3. So, Pint Man, Snowy Fox, Bob. Doing well there. Frosty, not so good. Okay, the faster you do it, the better, but you've obviously got to get it right. What was the programming language that was to blame for the BA hack? C++ is responsible for most of the problems in this industry. Buffer overflows, buffer underflows, heartbleed, and so on. But it wasn't, in this case, the problem. It was something else, I think, that outlined. And the problem was in JavaScript. Yeah, JavaScript. And it causes so many problems. So who got that one right? Well, of course Bob would get it. No Alice there. JB, Pint Man. Bob. Who's Bob? Bob? Is it you? Oh, well done. Good. I can see a 90% coming here and here. For an A, what's the most common substitution for an A in passwords that Hashcat would identify as an A? Is an O, a star, an at. Oh, wow, perfect. There we go. You were listening, weren't you? When I was talking about passwords, you were listening, but not when I was talking about symmetric key encryption and blockchain and things. Okay, so who was the fastest this time? Snowy Fox was very fast. Frosty did well. I think it might still be Bob. No, it's Snowy Fox. No, it's still Bob. Well done, Bob. Bob. But it'd be Bob with the number at the start, and then you would have an uppercase at the end, of course. So you didn't get your name right there. Okay, fastest. It gets more points. And what's a possible mapping? God, this is going to melt your brain. What's a possible mapping for hello with a Caesar cipher? I know that's horrible. That's horrible. Of course it's horrible. But do you have a quick brain? Do you have a brain that approximates? Does a quick... Try and get that approximation. Whoa, there we go. Oh boy. Did Bob get that one? Oh, no. Did you get that one? No. I'm shocked. Who were the two people that got that one? Okay. Oh, that was amazing. Well done. And the other person wants to hide. Okay, so we'll find out who got that one. Oh, are you JG96? Who's JG96? Crab? Who's the crab? That's you. Well done. Okay. Oh, you're still not top. That's a real shame from there. Okay, right. Get ready. If you have a 10 billion passwords to try and have a cracker that does 10 million hashes per second, how long will it take to crack? Oh my God! Oh, it's only the start of the semester. And your brain just melts. Steadily. Can you quickly approximate things? Sometimes you've got to do that. There we go. What did you think it was? Everybody's voted. Oh, right in the middle. Yeah, 1,000 seconds. Well done. That's really good. Really good. I don't know how you did that, but that was really impressive. So Frosty did well. Pint Man back in there. Snowy Bob. What happened, Bob? Bob, you're crashing here. Oh, Snowy Fox. Who's Snowy Fox? Oh, well done. Snowy Fox is way in the lead now, so you're going to struggle. You need to improve yourself. Who's L? You can't put your name. Is it you? Is it you? No, behind. No. Okay, I'm recording all your MAC addresses, not so I'm not going to do that. Okay, get ready. You're struggling now. If we go from AA to ZZ, how many passwords are there? Just lowercase. Just trying to approximate this one. We will do this with Hashcat, and we will try to estimate how long Hashcat will take to go through this is a brute force attack, and it must go through AAA to ZZZ, and the answer is 17. Oh, that is really impressive. I'm gobsmacked. 26. Yeah. Well, come along to lecture 3. Okay. 52. Come along to lecture 3. And you'll find that those aren't the right ones. So if I'm cracking AAA to ZZZ, then it'll take 17,000 along the way. So Bob, did Bob get that one? No, what's happening, Bob? You're falling apart there. Oh, Bob, you're still doing well, but not so well. Still Snowy Fox, Frosty. Who's Frosty? And Snowy Fox wins. Who was Snowy Fox? Who's you? Oh, done. That was excellent. We're not worthy to be in your space. Bob, that was so disappointing. You'll have to improve. And I thought you were really in there, so I'll be looking for Bob and the two to do really well the next time. Okay, so every week, this has got nothing to do with the assessment and the modules, but we'll have a bit of fun and see how you get on. So we'll have a lab now from 11 to 1. We've also got another lab booked for 1 to 3 if you want to hang on, if you've got any questions. But please come along to the lab today and we'll get you set up from a practical point of view. Main thing, Python is what we're looking at. We don't want to be super duper coders necessarily, but at least to understand how we can articulate our crypto in Python. Okay, well, thanks very much. Everybody signed the register? Good, right. I'll see you in the lab then. Go and have a coffee and maybe we'll start the lab about 5 past or so, or 10 past 11. We'll get you set up in C27. Okay, thank you.